Hi, everybody. So this is the first of 7 videos on heaps. In this first video, we're going to talk about the motivation behind this data structure that we're going to study and see why we want to use it, what is the advantage, and so on. So before we talk about heaps, I want to talk about an idea called a priority queue. Okay, so we talked about queues before. Queues was that data structure where we said, okay, if we take something and we insert items in order, then when we take it out, it will come out in the order that it was inserted, first in, first out, right? And we talked about how to implement queues with arrays, with linked lists, and so on. So today I want to introduce you to a slightly different kind of queue. So the kind of queues that we studied so far, the FIFO queues, are basically the kind of queues you might find in a supermarket. You go to a supermarket, you have to check out, you wait in line, and then everybody who is in line, they basically are checked out in the order at which they entered the line, right? So they just go through the line, and one person at a time goes through and gets checked out, and so on. So that's pretty much a queue, okay? Um, Now, priority queues, however, are slightly different. Priority queues are the kinds of queues you might encounter in, for example, a hospital emergency room. If you were to visit a hospital emergency room, you don't get processed, like you don't get to see the doctor based on the order of your arrival. You actually get to see the doctor based on how sick you are relative to everybody else in the emergency room. So if you go in and you broke your arm, it hurts, sure. But if somebody's having a heart attack, they will probably get seen by a specialist before you because they might die. And as much as your broken arm hurts, you're not going to die from it. So that's pretty much priority queues in a nutshell. That when you put things into a queue, the order with which it is processed, the order with which items come off the queue, isn't necessarily based on when an item entered, but instead is based on some idea of priority. Okay, so you take an item, you say this is priority whatever, this is the highest priority, this is the lowest priority, and as it enters the queue, it is placed into the queue with priority in mind. Now, let's imagine us having to write this priority queue object. So again, we have this abstract data type called a priority queue, where we put things into the queue, and we take it out, we process each item. The thing that we care about is based on which one has higher priority. We have 3 basic functions that we care about. Your standard, put something in, push. You have something that where you take something out, pop, and front. Okay, so we're just using the same terminology. Put something in, take something out, and whoever's at the front of the queue. Same idea as a regular queue. It's just that instead of thing at the front comes out, it's highest priority thing comes out. Instead of whoever's at the front of the queue isn't the thing that was in the queue the longest, it's the highest priority item is at the front of the queue. Okay, so this is the idea. Now, if I ask you so I want you to take a moment, pause this video and think, okay, I want to write this class. I want to write a priority queue class. What is the underlying data structure you would use to create this thing? How would you actually do it? Okay, so pause the video and write down what your answer would be. How would you go about implementing the priority queue? Start now. Okay, so hopefully everybody's had a chance to sort of think through how they would implement it. I'm going to go through a few ideas. I'm going to draw out what the consequences of the 3 operations are given these ideas. Okay? So let's let's use an array. Okay? Because arrays. So, and in particular, because I care about priority, I'm going to use a sorted array. And it's going to be sorted by priority. Okay, so instead of being sorted by value, it's sorted by the priority of the object. So we somehow have a way to assign priority to an item, and we sort it based on its priority. Okay, now for implementational reasons, we are actually going to put highest priority item at the back of the array. Why do we want to do that? Well, think about how fast it is to remove something from the back of an array. So if you have a bunch of items, right? We know that if we wanted to, remember with a stack, we said, okay, we take things, we put it in, we fill up the array. And if I wanted to remove the thing at the back, it's relatively simple. If I'm tracking the size, right? Remember, or the number of items that are used, right? So right here, the number used is 6. So if I wanted to remove something, it's simply a matter of removing, changing this number down to 5. And it's like, oh, this one doesn't even exist, right? So it's relatively fast to remove something from the back of an array. It's actually a lot slower to do it from the front, because if I wanted to remove the first item, I would actually have to take each of these and I would have to shift it over by 1. So that's why we do it this way. It's actually faster. And you go, okay, so great. So we put the highest priority at the end. Now, so we've kind of taken care of that. Now, obviously, we have to maintain the sortedness. So when we put something in, we can't just put it in anywhere we want. We actually have to put it in based on priority. Otherwise, the highest priority item won't be at the back, right? So we have to keep it sorted. Now, what does that actually do to us when we are putting data in and removing data, and also for front? What is the runtime of each of my operations? Now, for push, this particular function, the push function, the push process. So let's draw it out, okay? So we have an array where we sort by priority. Now, first of all, what does priority mean? Well, priority is simply some way for us to identify who is more important. Now, unfortunately, that's somewhat, it's not always clear. So, for example, we can say the highest number has the highest priority, bigger, more priority, right? Or we can say the lowest number is higher priority, like we're number one. Number one is priority, right? So what do you mean by this? So for now, we're going to use consistently in this first set of videos, we're going to do lowest, we're going to do smaller number, higher priority. So in other words, 1 is the highest priority, 2 is the second highest priority, and so on, okay? Smaller number, higher priority, okay? And it just makes it easier. We don't care about the data, by the way, in this case. It's really the priority values that matter, so I'm not going to draw the data in. I'm only going to be putting in the priority values. So if we were to implement this idea, then what will happen is we will put the highest priority number values at the end. So for example, 1, 6, 8, 10, 15. Okay, 1 is highest priority. Okay, 1 is highest priority. Okay, 15 is currently the lowest. Okay, now how do I put something into the queue? Now, so if I were to take a new value, which I will draw here, so this is a new value that I want to put in. The value I want to put in is 7. Okay, what is the process of putting 7 into my priority queue? Now, let's not even worry about growing our array or not growing the array. Let's assume that our array is infinitely large and has infinite amount of space. Okay, let's even assume that there's a lot of space over here. Okay, putting the 7 in is actually going to involve doing the following. We're going to have to say, okay, can I put the 7 right at the beginning? Is it the most important item? Can we put it right here? Right? Is this where, can we put it in this spot right here? And the answer is no, you can't, because 7 is not higher priority than 1. So we have to take the 1, move it along. Can we put the 7 into the new available spot? And the answer is, well, no, that spot's not available either because 6 is higher priority. So you have to move the 6 along. Oops. Move the 6 along. And then finally, can I put the 7 in the empty spot now? Can I put it here? And the answer is yes, you can. Okay, so you can put the 7 in. Now, at worst case, this process of moving the 7 around is actually going to require a total of n steps. Okay, this is n because we need to find the place to put it and put it in. Excuse me, moving it. Okay, so I know, if you've watched the video for lab 6 and 7, remember we talked, so you say, wait, no, the array is sorted. We can binary search for the right place. But remember what the video says. If the array is small, binary search isn't necessarily the faster way to go because of branch prediction, right? So you kind of have to watch out for these things. But in any case, it doesn't matter. It's moot because even if binary search is faster, even if we could find the place really fast, the insertion into an array is going to cost us on because we have to shove everything over once we do find the place. So yes, you can say, okay, I can find the location faster if I do binary search. I'll even give it to you, even though it's not true for small arrays. Okay, let's give you that. Even if you could do that, finding the right, actually placing the value in, that process is going to cost us n because we have to move everything over to fit this one thing in. We don't know where it's going to go. It's not necessarily at the front, so we can't use that trick we did with queues where we sort of had a front and a back because it's not guaranteed that the item that we're inserting, like 7 in this case, is at the back. So the only way to deal with this is to move everything over, and that's going to cost us n. Okay, so there's no way around this. It's going to cost us n no matter what. Okay. What about pop? Well, if our highest priority item is at the back of the array, then popping is relatively straightforward. We just reduce the size. And so we can say that this is going to cost us O1. Okay, push is ON. What about front? Front is find the highest priority item. That's actually pretty fast. It's actually O1 because it's just whatever's at the back of the array. Very fast. Yay. So we've got a slow push operation. But it's fast on pop and front. So there's some advantages to that. So is this the best that we can do? Well, let's see if there's better solutions, right? So you go, okay, well, you know what? So let me just be clear on this. So right here we said, okay, if we find the place to put it in, then putting it in that's what the slow part is. Well, what if we use a linked list, right? A sorted linked list. Sorted by priority. And in the case of a linked list, it actually doesn't matter if the front or the back is going to be is the highest priority item. As long as it's doubly linked. If it's singly linked, then the front item has to be the highest priority item because pop back is so slow, right? So we'll sort it by priority, okay? And just so that it's easy for us to talk about, we're going to say that we put the highest priority item at the front of the linked list. That way, even if the linked list is singly linked, this is still fast for pop, okay? Now, push, data, pop, and front. What are the costs of each of these? Well, putting something in, this is actually still ON. And why is it ON? Because insertion into the middle of a linked list is actually O1, right? Like, why is this going to cost us so much? Well, here's the problem. So here's the same priority queue, So here's the same priority queue that we had before. Okay, implemented using this idea of a linked list. How many items do I have? 5. Okay. 1, 6, 8, 10, 15. Okay, so basically the same queue. Okay, implemented slightly, so implemented differently, but it's the same queue. Okay, we have pointers backwards and forwards. Okay, now if I want to put in the 7, if I knew that this was the place to do the insertion between 8 and 6, insertion is relatively simple. I take this pointer and I point it over here. I take this pointer, point it over here. This pointer over here points this way, and the backwards pointer points to 6, and that's it, right? It's actually constant. Okay, so the insertion piece is constant, because no matter how long this link is, for me to unlink this node, given the fact that I know that it goes before this node, I can do the linking and the unlinking and putting the 7 in constant time. I can do that very fast. However, okay, finding where to put the new node is ON. Why? Because if I wanted to figure out where 7 should go, I have to start from the beginning and say, oh, do I put it in front of the 1? Yes, no, no. Go to here. Can I put it in front of the 6? Nope. Then I go to the next one. Can I put it in front of the 8? And the answer is yes, because it's smaller. I put it in. But actually finding the location itself is an ON operation. You cannot binary search a sorted linked list. So there's no way of doing the find anywhere faster than ON time. So even though the actual insertion is only O1, the total cost is still ON, because when you have two types, when you do two things, it's the one that costs more that dominates over the part that costs less. Okay, so if you have two independent operations where doing something doesn't change how much it costs to do the other thing, then you take whichever one is slower and you say this is the cost of the total. And so the cost of the total of putting the data in is N. What about pop? Well, popping, this is pop front, right? Which we know is O1. So that's good. Front, well, this is just getting the very first note. We know this one is O1, so that's great. So we still have a problem on putting something in because we have to figure out where things go, right? Well, what if we don't? What if we just have an unsorted array? Like this seems like it's going to cost me too much. Why don't we just put it in at the back? So how about an unsorted array? What will this do for us, right? So we just take things in, we push add to back of array. Well, this is going to cost us only O1 to put in. Yay! Except that if we put it at the back of the array, where is the highest priority item? And the answer is you don't know, because it could be anywhere in the array, anywhere. So we don't know where the highest priority item is, so what do we have to do? We have to find it. And that cost is going to be ON, to find highest priority item, and then shift to remove. So what do I mean by that? So if I had to get the same numbers, 1, 6, 18, 5, whatever, into my array now, okay? Now, when I inserted it, it's just the order of insertion, right? Like a regular queue. So 1, 6, 10, 15, 8. They could have gone in any order. I don't know what the ordering is. Adding 7 to this unsorted array is easy because I don't care about sortedness. I just stick it in at the back and we're done. Very fast. Unfortunately, when I want to try to remove an item, I cannot guarantee where the highest priority item is. Now, this one happens to be at the very front, but it could have just as easily been here, right? Like this could have been 15. So I don't know what the highest priority item, where it's going to be. And even if I find it, okay, even if I know, like, so even if we go back to the original situation where one was at the very beginning, let's say it's there. After I know where it is, I still have to get rid of it. And getting rid of it involves basically shifting everything over. 6, 10, 15. Everything must be shifted. And remember that this could have been in the middle of the array, right? So if we have to shift everything, that's going to cost us ON, okay? And since we don't know where it is, we might have to shift everything. Okay, we can't just like in queues, you know how you use the pointer to the front? You can't do that because you don't know that the item you're removing is definitely at the front. It could be the second item. Then what? So we have a bit of a problem here. Okay, spelled this wrong. Sorry. Sorry. So the highest priority item is shifted and removed. Now you also have front. Front, this is actually also ON. To find highest priority item is going to cost us a search the entire list. We don't know where it is. We don't know that the first one that we look at is the highest priority. So you have to look for the entire list looking for the smallest item, which is a problem also. So we've got this idea of an unsorted array, but if we do that, then now we have the push function is fast now. That's fast. But we've done it at a cost of making both pop and front really slow. So both of these are now ON, and that's problematic because now we still have the same problem as before. So none of these solutions seem very good. And by the way, if you use an unsorted linked list, the same problem will occur. Finding something is going to be the thing that's slow. So none of these solutions look like it's offering anything better than all three. None of these solutions offer a solution where all three of them are fast, because ON is not really fast since it grows with the size of the data set. So can we do better? Can we get something where every single operation is going to be less than ON? And the answer is yes. Yes, we can do this, but not with just a simple sorted list. Okay? So the data structure that will actually allow us to implement a priority queue quickly is a data structure called a binary heap. Okay, so so we are going to study a data structure now called the binary heap. Okay, now there are other kinds of heaps, but in this course, since we're only studying one heap, we will refer to this as heap. Okay, while there are other other heaps, other types of heaps, this course will only talk about binary heaps. So when we talk about heaps, it's always binary heaps. Okay, so there are actually other kinds, and their implementation gets a little bit more interesting. But for our purposes, we don't need to talk about them. We will just look at binary heaps only. Okay, so if I talk about heaps, it's always the binary heap. We're not talking about some other data structure out there, just this one. Okay, so what is a binary heap? What is it? What is the definition of a binary heap? So a binary heap is a data structure of the following nature. It is a complete binary tree where the heap order property is maintained, which then leads to it should lead to now at least two other questions. What on earth is a complete binary tree, and what is this heap order property that you speak of? So that is going to go into the next video. Okay, so in the next video, we will talk about basic definitions. What is complete binary tree? What is heap order property? How do we make a heap? Okay, and implementation and so on. We'll go into future videos. Okay, so we stop here for now. That's it. Thanks.